Welcome to this session on the taxonomy of ionizing radiation sources. In nuclear medicine, we often use radiation every day, but it is important to think of all sources in an organized way rather than an isolated examples. In this lecture, we will classify ionizing radiation into major groups such as fast electrons, heavy charged particles, electromagnetic radiation, and neutron sources, and then connect those categories to source behavior, measurement, and practical use. The goal is not to memorize names but to understand why each source behaves the way it does, how it interacts with the matter, and how we choose it for a specific task in imaging, calibration, or radiation physics. Let us begin by characterizing the radiation landscape. A useful first step is to ask whether the radiation is charged or uncharged, and whether it is heavy or light. Heavy charged particles such as alpha and fission fragments have very short penetration because they lose energy intensely over a tiny distance. Fast electrons such as betas and convergent electrons travel farther but still have limited range compared with photons and neutrons. Electromagnetic radiations like gammas and X-rays and neutrons can penetrate much more deeply, which is why shielding and detector response are so different for each class. In the laboratory, we commonly deal with sources spanning a wide energy range from electron volt level to many mega electron volt. So this broad classification helps us predict behavior before we ever measure it. Now we move to source mechanics, especially the ideas of hardness and self-absorption. Some sources need to be prepared as very thin deposits, sometimes even unencapsulated, because the emitted particles would lose too much energy if they had to pass through source material or an outer cover. That is particularly important when we want to preserve a monoenergetic or nearly monoenergetic signature. Other sources are much more forgiving and can tolerate thicker material or encapsulation with minimal distortion of the spectrum. So, when we think about source design, we are balancing physical durability against spectral purity, and that balance depends on the type of radiation involved. To discuss radioactive sources properly, we need a common language for measurement. And one of the key quantities is activity. A specific activity describes activity per unit mass, and it depends on the decay constant, Avogadro's number, and the molecular weight of the sample. In practical terms, this tells us how much radioactivity is packed into a given amount of material. The historical unit is the curie, while the SI unit is the becquerel, where 1 becquerel means 1 disintegration per second. High specific activity is often desirable because it reduces self-absorption inside the source and helps preserve the emitted spectrum. Energy is another basic language we use all the time in radiation physics. 1 electron volt is a very small unit of energy, but it becomes extremely useful because it matches the scale of atomic and nuclear processes. We use it to describe X-rays, beta energy, gamma rays, and many detector calibration sources. Since photon energy is related to frequency through which the equation E equals h divided by nu, sorry, since the photon energy is related to frequency through the equation E equals h nu. The same physical principle links electromagnetic radiation across a huge range of the spectrum. In radiation work, it helps to keep the scale in mind. EV for atomic interactions, KeV for diagnostic X-rays, and MEV for nuclear processes. That energy ladder is one of the most important mental models in nuclear medicine and radiation physics. Fast electrons from beta decay produce a continuous spectrum, and that is one of the defining features of beta emission. The reason is simple. The decay energy is shared between the beta particle and the antineutrino. So the electron does not come out with one fixed energy. Instead, the spectrum extends from very low energies up to an end point, which equals the Q value of the decay. In the example of chlorine 36, the end point is about 0.714 MeV. This continuous distribution is why beta sources behave differently from gamma or alpha emitters, and why endpoint energy matters when we are considering shielding, detector response, or calibration geometry. Internal conversion is another important way to generate fast electrons. But here, the mechanism is different from beta decay. Instead of emitting a gamma ray first, the nucleus transfers its excitation energy directly to an orbital electron. That electron is then ejected with a discrete energy determined by the nuclear transition energy minus the binding energy of the electron shell. This gives characteristic electron groups often associated with K cell or L cell conversion. In practical terms, internal conversion is very useful because it provides laboratory scale monoenergetic or near monoenergetic electron groups for detector calibration in the keV or MEV range. Alpha decay belongs to the class of heavy charged particles and is very different from beta emission. Here the nucleus emits helium-4 particle, and because the alpha particle is relatively massive and doubly charged, it loses energy very rapidly in matter. The emitted alpha particles from common sources such as Am241, americium-241 or Cm244, curium-244 have well-defined energies, typically around 5 to 6 mega electron volt. Because these sources are so easily degraded by material in front of them, they are often prepared as very thin bare deposits. That design requirement is not just a technical detail. It is essential if we want to preserve the monoenergetic quality of the alpha emission. A spontaneous fission produces a very different kind of heavy charged particle source. In this process, a nucleus such as californium 252 splits into two major fragments with a broad distribution of kinetic energies. The split is usually asymmetric, producing a heavy fragment group and a light fragment group. These fragments start out highly charged, which gives them an enormous stopping power and a very short range in matter. That is why spontaneous fission fragments represent some of the most strongly ionizing particles in standard radiation sources, even though their practical range is quite limited. Gamma emission is the classical example of electromagnetic radiation from the nucleus. Unlike charged particles, gamma rays arise from transitions between discrete nuclear energy levels, so their energies are sharply defined. Cobalt-60 is a familiar example, where beta decay leads to an excited nickel state that then emits gamma photons at characteristic energies. Because the excited state is short-lived, the gamma ray essentially reflects the half-life of the parent radionuclide rather than a long-lived intermediate state. In nuclear medicine, this concept is central to source calibrations, shielding design, and understanding the photon energy spectrum of radionuclides. Two other important electromagnetic processes are inhalation radiation and X-rays. In positron-electron inhalation, the positron and electron convert their mass into two photons of 0.511 MeV each, emitted in opposite directions. That is the physical basis of PET imaging. X-rays, on the other hand, may be characteristic or Bremsstrahlung in origin. Characteristic X-rays come from electron rearrangement after inner shell vacancies, while Bremsstrahlung is produced when fast electrons are decelerated in matter. For students, the key point is to distinguish line spectra from continuous spectra and to connect each to its physical mechanism. Neutrons from spontaneous fission have a broad energy distribution that is often described by the Watt spectrum. In practical terms, that means the neutron energies are not monoenergetic, but instead peak in the sub-mega electron volt region and extend up to several mega electron volt. Californium 252 is a common example and is notable for its high neutron yield per microgram of material. Because neutrons are uncharged, they interact differently from photons and charged particles, which makes them especially important in shielding studies, activation work, and specialized detector calibration. Their presence also means that prompt gamma emission must be considered together with the neutron field. Neutrons can also be produced by target reactions, and there are two major pathways to remember. In alpha N reaction, an alpha particle interacts with a light nuclei such as beryllium, and because the alpha loses varying amounts of energy before reacting, the resulting neutron spectrum is broad and continuous. In photoneutron reactions, a gamma rays a gamma ray interacts with beryllium and produces neutrons that are much closer to monoenergetic because the gamma either interacts or it does not. This distinction is very useful in source selection because the reaction pathway largely determines whether we get a broad neutron spectrum or a relatively narrow one. Let us now turn to the source selection matrix. Whenever you choose a source, you should ask what particle type is needed, what energy range is appropriate, and whether you need a monoenergetic source or a broad spectrum. You also need to consider practical issues such as activity, self-absorption, encapsulation, range, and shielding requirements. In nuclear medicine and radiation physics, the best source is not simply the most intense one. It is the one that matches the measurement objective, the detector response, and the safety constraints of the setup. This matrix is a useful checklist for making that decision systematically. I would like to close by emphasizing the main lesson of this lecture. Ionizing radiation is not one uniform entity. It is a family of source types, each with its own mechanism, spectrum, penetration, and practical use. Once you understand whether a source is charged or uncharged, heavy or light, continuous or discrete, you can predict much of its behavior before looking at single measurement. That kind of thinking is especially valuable in nuclear medicine, where image quality, detector calibration, shielding, and radiation safety all depends on choosing the right source for the right purpose. Thank you.